This is section 10.2, diagonals and angle measure. For a while now, we've known that triangles have 3 angles and their angle sum adds up to 180. So for example, I'm just making these numbers up. Let's say that's 50, maybe that's 60. That's gonna leave that guy at 70. Those 3 measures have to add up to 180. If you have a shape that's not a triangle, like a quadrilateral, for example, you can draw a diagonal on this quadrilateral and make it into 2 triangles. And we know there's 180 degrees in each triangle. So quadrilaterals have 360 degrees total for their interior angle sum. And we could do the same thing for every single shape. There's a pentagon. If we would draw some diagonals on the pentagon, you end up with 3 triangles, 180 degrees in each one. So that means pentagons are made up of 3 triangles for a total of 540 degrees for the interior angle sum. Okay, now if we keep doing this, we can calculate interior angle sums for every single polygon. Okay, so we're going to keep going with this process. What's the angle sum for a triangle? We know it's 180. How many triangles are in the octagon? Okay, well, we can count them. I don't know if green's the best color there. There are 6 triangles in an octagon. So what would the interior angle sum be for the octagon? Well, 6 triangles times 180 degrees gives you 1,080. So every octagon in the world has that interior angle sum. Okay, now there's a pattern that's forming. If you take into account these 3 examples and the one that we just did, you should notice that the number of triangles inside of a polygon is actually 2 less than the number of sides. And that's where this theorem comes from. This is called the polygon angle sum theorem. It says if a convex polygon has n sides, then the sum of the measures of its interior angles can be found by taking the quantity n minus 2 times 180. Now, we know the angle sum for all triangles is 180. So if we're calculating interior angle sums for triangles, you put a 3 in for n. 3 minus 2 is 1, and 1 times 180 is 180. So what's your interior angle sum for a quadrilateral? Well, we already calculated it, but what you would be doing is entering 4 in for n, because quadrilaterals have 4 sides. Okay? And that'll give you your answer of 360, which we already calculated. We already calculated for pentagons also. 5 sides in a pentagon, so put 5 in for n. It gives you a sum of 540. We could do the same thing for hexagons. We'll put 6 in for n. So 6 minus 2 is 4. 4 times 180 gives you 720. So every hexagon has 720 degrees. Now, we're going to skip heptagon, which is a 7-sided shape. Octagon, we already calculated. We know it's 1080. We could jump right to decagon. So the nice part about this theorem is you can jump to any shape you want. You don't have to go in order and keep adding 180 degrees because you get an extra triangle for every shape. So 10 minus 2 would give you 8. And 8 times 180 gives you 1440. So every decagon in the world has 1440 degrees. Okay, so that comes in handy when you're solving for angle measures for shapes, and you know all of them except for one. So here's an example. Name this shape. So we have to count the sides or the vertices. I'll give you the same number. There's 7 sides, 7 vertices. So this guy's a heptagon, which works out nicely because we didn't do the heptagon on the last slide. Is this a regular polygon? Well, you can't tell unless there's marks on it. I think I meant for it to be regular. Okay, so take a moment and just make those marks on your notes. You're marking all of the sides congruent and all of the angles congruent. Remember, polygons could be equiangular and not equilateral. They could be equilateral and not equiangular. So we're going to say this is regular. What does that mean about the angle measures then? They're all going to be congruent. What is the interior angle sum for a heptagon? Use your theorem. We're going to put a 7 in for n. So that means there's 5 triangles. That'll give you an interior angle sum of 900. And if all 7 angles are the same, what's the measure of each angle? So you got 900 total. All 7 are the same. Each angle has to be 128.57 degrees. And it's okay to get decimals. It just means it's in between 128 and 129 degrees. So let's keep going with that concept. We're going to look at regular figures. All of these shapes here are going to be regular. So you're going to handle this one just like we did on the previous problem. What's the measure of one interior angle of a regular nonagon? So we're going to calculate the interior angle sum first. That'll give us 1260. All 9 angles are the same. So what's the measure of each one? 140. We'll do the same thing for a 14gon. Put 14 in for n. That means there's 12 triangles. That'll give you a total of 2,160 degrees. We're going to divide that by 14 because all 14 angles are the same. That's going to give you a decimal again. It's natural to be skeptical. That doesn't mean you're wrong. Okay, and we'll do one more. One interior angle of a regular hexagon. Okay, now once you do these shapes time and time again, you'll get tuned into the interior angle sums. I know that's 720. And if they're all the same, divide by 6, that means each interior angle is going to be 120 degrees.